In this video, I'm going to show you how I made an AI play Snake game using Stable Baselines 3 and OpenAI Gymnasium in under 10 minutes. Credit where it's due, I got a fair bit of the code from Mr. David Gushezhnov in his Towards Data Science article. Lastly, I will assume familiarity with basic Python, NumPy arrays, and reinforcement learning. Now let's get started. First, imports. We'll use NumPy arrays to build the grid of the game, matplotlib to render the animations, and OpenAI Gymnasium to build the environment. Next to the skeleton for the environment, we will build a class for the snake game, which inherits from OpenAI Gymnasium. We initialize the environment in init, observations are the inputs to the reinforcement learning model, step is where we define the possible actions the agent can take, reset is how the agent will prepare the environment for the model to run. We will also define functions grid distance, snake plot, and render to be used a little later. We start with the snake game class, before the init. I'll talk more about metadata later when we build the render function, but for now, let's just set these two modes, console and RGB array. We want our snake to have 3 actions available: keep going straight, turn left, or turn right. As I mentioned, the snake game itself is represented by a NumPy array making a grid, and its values will be a 0, 1, 2, or 3, representing empty spaces, snake tiles, walls, or food. Next up, rewards. As with most reinforcement learning models, the goal of the agent is to maximize its reward. In our case, we will reward the agent for steps towards the food and actually getting food, while we'll punish the agent for dying. Finally, to avoid infinite loops, we'll set a maximum number of steps without food at 200. Before we continue, let's quickly define the grid distance function, since we will use it in the init method. We want to record the distance between any 2 points on the grid. To do that, we'll quickly fill this function with a NumPy command linalg to find the distance between 2 points on the array. Now for the init method. The goal of the init method is to initialize the grid that the agent will play on, define the action space, and define the observation space. We set the grid size to 10 for some relatively fast training that still looks good. We are counting steps as well, so that we can cut it off if there are too many steps without food. Then we build the grid, with walls surrounding the edges, the snake in the top left corner, and food a bit closer to the center. We also want to record the distance from the snake's head to the food, since we give the agent reward every time it gets closer to food. We copy the grid and coordinate values, so we can manipulate and use these later without changing the originals. And now we're ready to move on to the spaces. We already defined n actions for how many possible actions there are, and the observations we want to give the agent are the position of the head, the direction the snake is facing, and the full grid. Now, the reset method. We're basically just resetting the environment back to its initial state. To do so, we reset the step num and food steps back to 0, and then reset the grid, snake, and distance values back to their initial states. We use the random seeding this way for convenience in training the model, but it's not too important here. If you want to learn more about random seeds, look up random B tables to learn more about how computers and calculators generate random numbers. Lastly, we want to return the observation and some information. There isn't any extra information for our environment here though, so we'll just leave it as an empty dictionary. In regards to the observation, we'll define the observation method now. Remember, the observations we want to give the agent are the position of the head, the direction the snake is facing, and the full grid. We can find the direction by just subtracting the head snake's coordinates by the coordinates of the snake body tile right before it. The position is just the head's coordinates, and the grid was previously defined. Now, the step function. We start by again finding the direction, and then testing the various actions. So if the agent tries to turn the snake right, we want the snake to actually turn right, and so on. We put the head in the new place, and add it to the snake coordinates list. Then we set done to false and reward to 0 by default. Setting a reward to 0 is important here, and it's also very important to note that this is not self.reward. As the agent goes along, it records how much reward it receives each step and adds this to its own internal total. We as the programmers do not have to keep track of its reward when using Stable Baselines 3. At this point, we have increased the snake size by default, whether it has gotten any food or not though. So let's fix that. First, we check if it has actually gotten food. If so, we need to reward the agent. Then we need to add more food wherever there is space. If there's no space on the grid, that means the snake is taking up 100% of the map except walls, so the agent wins the game. We can set done to true then. If the agent did not get any food, we remove the snake extension and perform a further check to ensure it has not died yet. If it has, we need to punish it. Assuming the agent hasn't died yet, we need to refresh the value for the distance between the snake's head and the food. If it's getting closer to food, we want to reward it, and if it's getting further, we want to punish it. Lastly, if it has been over the maximum allowed steps without food, for us that's 200, we want to kill the snake to avoid infinite loops. Two functions left, render and snake plot. We'll start with snake plot. First off, we get the indices of the walls, snake body, and food in the grid. Then we build a 3D color array using NumPy. Walls will be shown as black, food as red, and the snake as green. We're choosing these colors using RGB. Something important to note is that the snake plot function is only for us to visualize in the render function. The agent itself never sees the color arrays. It only sees the numbers that make up the NumPy array grid, which is why it will be able to train very quickly. Now finally, render. The function itself is very simple. If you want to see results in the console, use mode console. And if you want to visualize the results as a snake game, use RGB array. You may recall that these are the values from the metadata at the start of our program. And in our case, all they really are is identifiers for the type of output you want to see. We're done creating the environment, and now we want to give it a quick check to be sure everything is working fine before we get started with actually training. We can use the built-in command given by Stable Baselines 3 to make sure the environment is in an acceptable format, and if we get no warnings, we're good to go. Two more things before we actually start training. We need a place to store the model and a model itself. To deal with storage, we set up a folder in our local directory with a simple OS command. Then we can wrap it with a monitor and apply a callback function to more easily keep track of the progress as the snake trains. Now for the model itself. The model we'll be using is a Proximal Policy Optimization Model, or a PPO, from Stable Baselines 3, and we'll use a multi-input policy. Also, if we already have a model from prior training, we want to start there instead of resetting the training each time. Finally, we've customized the model arguments to speed up learning. The learning rate is the rate at which the model will make changes to its algorithm. Gamma values range from 0 to 1, and they're a measure of how much to prioritize future rewards. Verbose allows for an even more detailed view of training. Seed returns to random seeding. Again, check out random B tables if you're interested in how computers and calculators generate random numbers. The entropy coefficient is a measure of how much exploration is encouraged, and the clip range affects the probability of actions occurring. With these arguments in place, let's train the model. 6 million time steps will give you a good idea if everything's working fine. My computer will take about 2 hours to train these 6 million time steps, though that time will probably be different depending on the strength and quality of your computers. Then we reset the environment and prepare a framework to save the results. The frames variable is a list that carries each frame that occurs in the animation one step at a time. Lastly, we want to visualize the animation into a GIF. Matplotlib's animation command that we imported in the previous chunk is very useful here. With it, we can easily save the animation as a GIF and view the progress of the AI. On screen now is a GIF of my snake AI after roughly a day of training. As you can see, it performs quite well and has even learned some strategies, though they are different from what we as humans are used to.